All right, we are deciding whether or not the product of each of these matrices is defined, and if it is, what its size will be, or dimensions will be. So the first one here, we have A times B. So what we might do is just start by actually going through and listing each of these sizes. So A is a 2 by 2, 2 rows, 2 columns. B is a 2 by 1, 2 rows, 1 column. C is a 1 by 2. D is a 3 by 1. E is a 1 by 3. And F is a 2 by 2. Note in F, the element here is 1/2. So it's 1, 5, 1/2, -2. So A times B is a 2 by 2 times a 2 by 1. The columns of the first matrix, A, is the same as the rows in the second, so this is possible. And we get a 2 by 1 out of it. B times A, this is a 2 by 1 times a 2 by 2. Note that these two values, the columns of the first, is not the same as the rows of the second. So this is not possible. It does not exist. All right, on AB, we had a 2 by 2 times a 2 by 1. Since these two are the same, it is possible. And then the values we use are these two, 2 by 1. All right, DE, this is a 3 by 1 times a 1 by 3. Again, the columns of the first are the same as the rows of the second. And so the matrix we get out of it is the rows of the first times the columns of the second. ED is a 1 by 3 times a 3 by 1. So we get a 1 by 1 out. BE, this is a 2 by 1 times a 1 by 3. Right, again, columns of the first are the same as the rows of the second. And so we get out what's left, 2 by 3. BC is a 2 by 2. A times G. Obviously there's no G, so let's use AF instead. This is a 2 by 2 times a 2 by 2. So we get a 2 by 2 out. E times F, this is a 1 by 3 times a 2 by 2. The columns of the first, E, is 3. The rows of the second, F, is 2. 3 and 2 are not the same. So this does not exist. And F times E is the 2 by 2 times a 1 by 3, which also does not exist. Going back to 1 and 2, just to point something out here, note that this is A times B and B times A, and we do not get the same answer for them. So one of them exists, one of them does not, which this is weird for us, right? If we take real numbers, like 4 times 5, we get 20. And if we take 5 times 4, we get 20, right? They both exist, and they're both the same number. That's because with real numbers, multiplication is commutative, right? Here, with matrix multiplication, A times B is not the same thing as B times A. In fact, they're so much not the same that sometimes one of them can exist and the other one cannot exist. That would also be true. Neither of them have to exist. One of them can exist, one of them might not. They both can exist, like DE is 3 by 3 and ED is a 1 by 1. They both exist, but they're different. Got two special matrices. One of them is the zero matrix and the other is the identity matrix. So first, for the zero matrix, we'll just do this one. So we get 1 times 0 plus 2 times 0. Right, so first number in the first row, 1 times the first number in the column, we get 1 times 0, 2 times 0. The second, then, we get 1 times 0 times 2 times 0 again. So that's the second, first row, second column. We get 3 times 0 plus 4 times 0, 3 times 0 plus 4 times 0. Every single number here gets multiplied by 0. And so the matrix we get out is 0, 0, 0, 0. Now, is that going to matter if the zero matrix comes first or second? And the answer is no. Right, we get all zeros again. Now the second one here is called the identity matrix. So 1, 0, 0, 1 is the identity matrix. It's a matrix full of zeros, except there are ones on the downward diagonal. And here, something else interesting happens. So we get negative 1 times 1 plus 2 times 0. That's our first element. And then we get negative 1 times 0 plus 2 times 1. And then we get negative 2 times 1 plus 3 times 0 and negative 2 times 0 plus 3 times 1. Negative 1 times 1 is 1, 2 times 0 is 0, so we get negative 1. Negative 1 times 0 is 0, 2 times 1 is 2, and we see that this is the matrix we get, which is exactly the same as the one that we started with before we multiplied by 1, 0, 0, 1. So the identity matrix is like multiplying by 1. It's not actually multiplying by 1, but that's what it works like in the problem here. Now the same exact thing will happen no matter what order that's multiplied in. So here, this multiplication is commutative. Right? Matrix multiplication in general is not. The zero matrix and the identity matrix are more. So this is a little bit different because it's not the identity matrix in that the diagonal of ones is not coming down, it's switched. So this also will do something interesting for us, but we will actually do it here. So we have 4 times 0 plus 3 times 1. We have 4 times 1 plus 3 times 0. We have negative 2 times 0 plus negative 1 times 1. And we have negative 2 times 1 plus negative 1 times 0. Again, as I pointed out the other day, there is going to be some pattern here as we do matrices. So you'll notice that the first element here and the element down here, right? 4 times 0, negative 2 times 0. That number should be the same if you're doing this the right way. The same here, 1 and 1, 1 and 1, 0 and 0. Now because the second matrix is zeros and ones, they do appear a few more times than normal, but in this column it should be zeros, in that column it should be ones, and so on. So we have 4 times 0 is 0, 3, 4, negative 1, negative 2. And so what did this do to our matrix? Well, it just flipped the two values, right? We had 4, 3, now it's 3, 4. We had -2, -1, now it's -1, -2. Here's just determining whether the matrices are defined. If so, we're going to state the dimensions. So all we're doing is looking at these two numbers here and here. If they are the same, then the matrix product is defined. So they're both 5s, so this is defined. Then the new matrix uses these two parts, so we get a 2 by 1. Again, on number 2, we're looking at these two numbers. They are the same. So the matrix we get out is a 1 by 2. Now number 3 is the tricky one. Right, we could have added these matrices. However, one of them is 2 columns of the first by 3 rows of the second. These numbers are not the same. And so for matrix multiplication, this does not exist. These are both the same. So we get a 4 by 1. These are both the same. So we get a 3 by 4. These are both the same. So we get a 6 by 5.